Yesterday we talked a little bit about how the solubility of a hydroxide is affected by the pH of the solution. And I want to delve into that topic a little more deeply today. You will not find this information in your textbook. So you probably want to make sure that you're taking some notes so that you can get anything down that I mentioned here, because you will be responsible for this information. We are going to be talking just in general about the pH of salts and what would make them more soluble or less soluble. Now you can tell whether the solution of a salt is acidic or basic based on the ions from which it is made up. So I've got a chart that is going to outline all of this up here. So if your cation is from a strong base and your anion is from a strong acid, an example of that would be sodium chloride. Sodium chloride would come from NaOH and HCl. Remember, an acid plus a base makes a salt and water. So sodium hydroxide is a strong base, hydrochloric acid is a strong acid, and so if I make that salt out of that, sodium ions and chloride ions don't react with water. There's no hydrolysis going on there. And so because there's no hydrolysis going on, that solution is going to be neutral. And so therefore, it's not going to make a whole lot of difference whether if I would try to dissolve it any better by making my solution acidic or by making it basic. The pH of it just isn't going to affect the solution much at all. Now, if, on the other hand, I have a salt from a strong base and a weak acid. So an example of that would be NaC2H3O2, sodium acetate. That is going to be made from sodium hydroxide and acetic acid. So a strong base and a weak acid. And the reason when I put those two together, that strong base characteristic is going to overshadow the acid characteristic, and the solution is going to be basic. Let's look at another example of how that works. Sodium carbonate is another example of a salt in this category. This is made from a strong base. Carbonic acid is a weak acid. And then when I put that into water, it dissolves according to this equation here. It's going to make sodium ions, which we already know do not react with water. And it's going to make carbonate ions. Now, carbonate ions, if you put them in water, will react with water. And so when that happens, water is the strongest acid that's around, and so it's going to donate the hydrogen ion over here. So I'm going to have HCO3 minus. And what's this going to have left over? Yeah, hydroxide ions. It's going to have hydroxide ions left over, and so those hydroxide ions are what makes that solution basic. What happens then if I add more base to this solution and I make the solution basic? Well, if you remember Le Chatelier's principle from your first year course, if I add more of this equilibrium wants to shift to try and get rid of it, and so it's going to shove the equilibrium back this way. So the shift goes back to the left to make more carbonate ions, which then in turn, if I have more carbonate ions here, this shifts this equilibrium back this way. And so therefore, I ultimately am going to have less that's going to be able to dissolve if I have a basic solution. On the other hand, though, if I provide some hydrogen ions for this carbonate to react with, so if I put it in acid solution, an acid is going to be a stronger acid than water is. Remember, water is going to flip either way. So if I put this one in something like a hydrochloric acid or a nitric acid solution, and I've got hydrogen ions here, the carbonate will choose to react with this as opposed to reacting with the water. And now what I'm going to have is HCO3 minus, but now I don't have that hydroxide ion being produced. So therefore, if I add more acid the equilibrium is going to shift to the right. Again, Le Chatelier's principle, add more this way. So the equilibrium shifts this way. More of this will be used up. So if this is used up, this equilibrium shifts this way also. And so therefore, in an acidic solution, more is going to dissolve. Okay? And so that's the reasoning behind why if you dissolve a salt from a strong base and a weak acid, it makes a basic solution if you just put it in water. Remember, you saw these hydroxide ions being produced here. But if I will put it in an acidic solution, more of that solution is going to dissolve because of the way the equilibrium shifts. Okay? I could do this same type of analysis on sodium acetate or any other type of salt that I want to use there. How about if I have a salt made from a weak base and a strong acid? So let's say that I've got NH4Cl, where my strong acid is hydrochloric acid, and then I've got ammonium hydroxide. In that case, the strong acid piece is going to take over, and the solution is going to be more acidic. And this is going to be more soluble in a basic solution than it would be in an acidic solution. Okay, so it's just the reverse of the one above. If you have a cation from a weak base and an anion from a weak acid, so if you had something like NH4C2H3O2, ammonium acetate, in order to determine what the pH of that solution would be, you would actually have to do some analysis based on the Ka's of all of the acids that are in, weak acids that are in solution. And so whichever one is the strongest one is going to be the one that's going to lend its characteristic to the pH of the solution. And therefore the solubility will depend based on what the answer is here. We're not going to get into that. If you take chemistry in college, I'm sure that you probably will, but we're not going to do it at this level. What I do expect you to know is basically the first 3 rows of this table and how things are affected there. Okay, I did give you some practice problems for today. I also am going to mention to you so that you don't get confused when you start the assignment for the next day, this section on, it starts on page 242 that talks about the technique of successive approximations. We are actually going to skip that section. Successive approximations is something that, from my understanding, is not taught until you are well into calculus. And so there are calculators available now that make it super easy to do those successive approximations. If you have to type all this stuff into the calculator, it's extremely tedious. It's not a technique that's used very often at all. And so I just have chosen that we're going to skip that section on successive approximations. So don't be alarmed the next assignment that you look at that it looks like we skipped over that section. I did it on purpose. And so we're not going to be covering that. So today I'm working on pH of salts and solubility, and then I'll see you back the next time.